Okay, guys, let's talk about negative and positive feedbacks as well as temperature and pH about for enzyme activity. So for the negative feedback, I think it's pretty straightforward to understand thanks to the slides. You can tell really easily that the substrate A here will allow to be changed. The enzyme allows the substrate A to be rapidly changed to B. Remember, A to B will happen without the enzyme just accelerate that, and that chain of protein of enzymes, you end up having B to C, C to D, D to the product, and that product will be then acting as a cofactor on the enzyme 1 to literally non-competitive or competitive. In that case, it's non-competitive inhibition. It could be competitive inhibition to prevent the enzyme 1 now to accept the substrate A and make more of the product. So why would you do that? Well, if you create enzymes for digestion, you may not want to create too much of it because you don't want to digest yourself when there is no food, right? When there is food, you may want to produce more of it. So that's a little bit tricky now because that's when the positive feedback gets in. So the negative feedback, we get it. If you make some products and you need a certain amount of it, you may want to stop producing it when you reach a certain amount. So when you start making product, at first there is not enough to inhibit all the chains because it's not only one chain, right, of enzymes. You have thousands of them. So you don't have enough products to inhibit all the enzyme chains. But at some point, the product is so highly concentrated that some of it will find its way here, right? Remember that if you have only a few molecules of product here, for them to find their place here, it doesn't happen naturally. Like they don't just have little legs and move around. That's temperature, the molecular movement making things move around. The more products you have, the more likely you will be to inhibit the enzyme 1 and stop the production of the product, right? That's negative feedback loop. You go back to the set point. You're trying to go back to the set point where you didn't have product, so you inhibit the production of product. Okay, the product can now deteriorate over time. The positive feedback loop, it's a little bit harder to understand, but it's the same principle. But instead of having at the end inhibition by competitive inhibition or non-competitive inhibition, now you have to think that the product will find its way to the enzyme 1, and then instead of changing the enzyme, the substrate site, the enzyme substrate complex, the site of the enzyme, instead of changing it into a way that's not allowing substrate A to fit, it's changing it into a way that makes the feet of the substrate A tighter, better. So substrate A was able to fit in enzyme 1 site, but it wasn't a perfect snug, it wasn't a perfect fit. The product is enhancing that fit into that site. So that's really what the positive feedback will be when you enhance the capacity of the enzyme to accept the substrate. You don't need to have the exact same shape. If the shape maybe doesn't have perfect of a deep here, a little bit too big of a deep, it allows A to come here, but doesn't really work very well. But it works. And with a product, you make a better fit, a snug fit. So that's really the key of positive feedback. Why would you want that? Well, let's say if you want your product to be used and you still need to produce it over and over again, you want more and more of it, what you end up doing is having that positive feedback loop. It's a run toward more and more product being made, right? So here you go, that's for the feedback. Now, if we think about what temperature and pH do to enzyme activities, look at this graph here. It's a meme. Guys, look at this graph. From low to high, the rate of reaction here on the y-axis and temperature from low to high here on the x-axis. If you see the increase in enzyme activity, the rate of reaction due to enzyme activity, it slowly increases to the peak and then it drops. The reason why it drops dramatically is all about the temperature and the hydrogen bonds. You reach a temperature at which the enzyme's hydrogen bonds start to break. And when that happens, the enzyme stops functioning. So when you reach the peak, it's peak and it's perfect. For a while, it still works, although some hydrogen bonds between the peak and the drop here, you see that there's some time. some temperature. Some hydrogen bonds break, but the active site is still okay, and the enzyme can still do its job, do their job. It's not perfect, but it works. And at some point, it's too much. The protein is denatured, as we call it. So when you cook your egg, remember, you denature the protein. You only have spaghetti noodles. It's only primary structure. It doesn't work anymore. Done. That's why there's such a sharp decrease here. That's temperature. pH does the same thing. Hydrogen bonds get disturbed by H pluses. The more acidic the solution, the more those H pluses, protons will break those hydrogen bonds to the point when it doesn't work anymore. So you have the same pattern for pH as well. And that's pretty much it for enzyme activity and how the positive feedback works. I'll see you next time. Take care.